Hi, everybody. Thanks for joining us for our next session of the day on multi-messenger astronomy. We have a panel today featuring 4 people who will be talking about different aspects of multi-messenger astronomy. And then we will have time afterwards for a group Q&A and discussion. The speakers will go back to back. You can enter your question at any time in the Q&A box, but be sure you specify the speaker to whom the question is referred. Thanks again for joining us for Chandra Frontiers in Time Domain Science. I'd like to ask our first speaker to share their slides. Our first speaker is Eleonora Troja from University of Maryland and NASA Goddard Space Flight Center, who will talk to us about X-raying compact binary mergers. You're presently muted. Good.
Okay, so thanks for having me again at this meeting. So today I will try to focus on what we can learn about compact binary mergers by studying them with X-ray observations. So I will start with our basic scheme of what is left over after a compact binary merger. Sorry. You see here at the center, we're going to have a compact remnant. This might be a neutron star. This might be an accreting black hole. And then this remnant is going to launch a relativistic outflow, which is responsible for the gamma ray radiation that we observe in many gamma ray bursts. And at later times, when this relativistic jet interacts with the surrounding medium, it will produce this broadband synchrotron radiation that we call afterglow. And it's visible across the electromagnetic spectrum from radio to optical and X-rays. And finally, there is a third outflow that is, second outflow that is very important. This is a slower moving outflow, but its composition is unique, it's very neutron rich, and is expanding very fast with a velocity of about 10–20% at the speed of light. And it is so important because we think that in this outflow, there are the conditions to trigger our process nucleosynthesis, which is the main responsible for the astrophysical production of the heaviest metals. And so from this outflow, we will see on a time scale of a few days, our optical infrared transient called kilonova. And so I will start with the main focus of the X-ray campaign of gravitational wave counterpart. That so far has been the afterglow component coming from the relativistic jet. And so what you see here is a view of multi-wavelength view of the afterglow. There are two main ingredients that are very different from standard GRB afterglows. One is clearly the temporal behavior, which is rising very slowly. And the other one is the luminosity. So at 9 days, when it was detected for the first time, the luminosity was of the order of 10⁻38 per second, which is several orders of magnitude below the typical luminosity of a GRB afterglow. And so this afterglow has been studied in extreme detail. But what I would like to point out today is that this is just one afterglow from one particular binary neutron star encounter. And so we actually expect from these systems a wide variety of outcomes. So even two neutron stars may lead to an accreting black hole, or they might form a massive neutron star as an intermediate stage. And this massive neutron star might either survive as a stable neutron star or finally collapse and form again a black hole plus torus system. And you see that all these different outcomes that you see here will leave their fingerprints on the observed electromagnetic signal. And therefore, that's why even if we studied in extreme detail this one event, we have so much to figure out by adding more events to the landscape. So here is an example of how the merger outcome might affect the afterglow behavior. So again, this is the GW170817 event. And I think many people now agree that this was produced by a structured jet, which is this jet with a luminous core and is less energetic and less fast material. And the reason this profile was so odd is because of the particular orientation we saw, we observed this object. But this is not the only possibility. So one other possibility is that, for example, a merger will not produce such a large amount of ejecta along its polar axis. And in this case, we might have the good old uniform jet, so without the structure. And so if that happens, we might see a very different behavior at the beginning with a much steeper rise of the afterglow emission and a similar fast decay at late time. Vice versa, we might have the opposite situation where the cloud of ejecta is so massive that the jet is not gonna make it out of it. So this might happen, for example, as you see, if the remnant is a long-lived neutron star, we expect the jet to be less energetic, so it might get choked by the polar ejecta. And if that happens, we see a completely different profile. So we see a X-ray emission that slowly rise, as we saw in this case, but the final decay is going to be much shallower. So this is just to illustrate how the future of afterglow observations might present a wide variety of behavior just because there are different mergers. And after that, I would like to focus on something else that is not the jet, because this has been the main topic for the past 3 years. And I would like to focus on how X-ray observation may open a window into the other components. So one is the merger remnant. We know that gravitational wave observation may give us an estimate of the mass of this remnant, but there is a wide range of mass values that leave this object undefined. It might be either a very light black hole or a very massive neutron star. So borrowing from what we learned from the GRB field, we know that this central object might leave its imprint in the observed light, and X-ray observations were actually a privileged window into the central engine. An example is what you see here, this very bright but short-lived X-ray emission, which might be due to a long-lived neutron star collapsing into a black hole. Again, another example coming from GRB afterglows are this rapid variation of the X-ray emission, X-ray flares, that we see both in long and short GRB to a less extent. And again, we think this is a probe of the central engine activity, so the central compact remnant. And finally, on longer time scales, we might see a rebrightening of the X-ray emission. So this is an example, again, borrowed from the GRB field. You see this X-ray emission in blue going down very rapidly. And then at about 2-3 days after the merger, we see the X-ray emission going up again. And so we think this might be due to the presence of a long-lived remnant that initially we did not see because the merger ejecta were opaque to its radiation. So it's initially hidden, but if we wait long enough, the merger ejecta may become transparent to this X-ray radiation, and we might see this weak X-ray flare after a few days. So this is an exciting opportunity to complement gravitational wave observations. And I would like to conclude this talk talking about the kilonova and how X-ray observations can actually contribute to the study of the kilonova, which was the main focus of optical and infrared observation at the beginning. But you know, depending on the model, we might actually see this component at late times in the X-ray range. So what you see here, again, is the GW170817 afterglow. And you see this dotted line is the jet contribution to the afterglow emission. And we are at a point right now where the jet contribution is becoming undetectable. And so what you see in this gray area is the posterior flux distribution that we expect from this kilonova afterglow. So what happens is that these merger ejecta that produce the kilonova at the beginning, they continue to expand. And so at this time, several years after the merger, their interaction with the surrounding medium might also produce a visible afterglow. And this afterglow is much weaker than the jet. So you see that most of the flux distribution is concentrated in this region, so it's quite faint. But there is a reasonable range of parameters that put it in this band, which is easily accessible by Chandra observations. And so why it is important to study this? Because as you can see here, there are several behaviors that we expect. And these behaviors are dictated by the properties of the ejecta, which in turn depend from the properties of the merger. So here is an example of how we can peer into the merger dynamics using these late time X-ray observations. So what you see here is a distribution of velocity for the merger ejecta for different equation of states. So when we observe a kilonova at the beginning with optical and infrared observation, more or less we probe this area, which as you can see is quite similar for many equation of state. But what is really different is this profile distribution of velocities, which might be either very shallow or very steep.
3 minutes.
Yeah. And so with our observation in X-rays at 2.5 years, so you can see this orange area shows the probability of each slope for the velocity profile. And as you can see, at this time, the constraints are not really meaningful yet. But by continuing the observations of this event for even a couple of years, we are going to achieve constraint that could be much tighter. For example, if the transient is going to be detected up to 5 years at the same flux level, then we could favor this steep velocity profile with much higher confidence than we can now. So I will conclude with the summary that the afterglow from the jet component has been the main star of the X-ray campaign of GW170817, but is not the only component that we can probe with X-ray observations. So it depends on the time scales and on the strategy that we are going to adopt with Chandra. But all these different components could be in principle constrained by Chandra observation or in general X-ray observations. X-ray emissions from the compact remnant, we expect it to be visible mostly in the early time region, in the early time interval. The jet, we know that it's going to be visible for weeks to months after the merger. And on timescales of several years, we expect to see this weak isotropic X-ray emission from the kilonova ejecta. Thank you.
Thank you, Eleonora. If you have questions again for the speakers, remember to put them into the Q&A and specify the presenter that you would like your question to be answered by, and we will answer those questions at the end of the session after all 4 speakers have spoken. I'd like to ask our next speaker to start sharing their slides. Our next speaker is Daryl Haggard from McGill University and McGill Space Institute, and is going to speak to us about preparing to prioritize and pounce in the LIGO-Virgo 04 era and beyond.
I made the title a little shorter to fit on my slides. So thanks for having me. It's a pleasure to be here with all of you. So I'm just going to talk a little bit about some of the things we've seen in our efforts to do gravitational wave multi-messenger astrophysics. I'm going to leave GW 170817 mostly to Raffaella and Eleonora, and I'm going to talk a little bit about our first candidate black hole neutron star merger today. So I want to start off just by sort of showing this nice multi-messenger matrix that Margutti et al., colleagues of Brian Metzger's who are here on the phone and many of yours, put together as a way of sort of trying to visualize what some of the different types of multi-messenger signals might be. We've heard about all of these in this morning's session and a little bit more during this panel today. So you're seeing a plot of remnant mass versus the type of signature, the gravitational wave signature. And then you can see these are sort of marked out with a little bit of, more English language interpretations here. Q is the binary mass ratio. So I'm going to really be focusing here on neutron star black hole and neutron star mergers. And I just want to say, that a lot of the talks we heard this morning involve some of the other messengers, neutrinos and cosmic rays, and those are also really exciting. And I think, as Brian alluded to in his talk, that some of these phenomena might actually bring many of these messengers to us, and that makes for a very, very rich understanding of what's going on with the sources. So many of you have already seen, I'm sure, the new 03 catalog that came out just yesterday. So this is for the first half of LIGO-Virgo 03. I knew yesterday exactly what that rate was, but they detected a lot of sources. So you can see this is this masses in the stellar graveyard plot that has been coming out of their collaboration for a little while. And all of these are the gravitational wave sources, the targets, the points in blue are black holes, and the points down here in orange are neutron stars detected via gravitational waves. You'll see a few question marks. These are sources where, again, as Brian talked about this morning, we're not quite certain whether or not we've had a black hole or a neutron star in the interaction. And when I first saw this, I was like, oh, that's beautiful, it's amazing, but what happened to all the EM sources? Because I'm really excited about the EM follow-up. And so here they are. They also kindly gave us that plot. So now we've got the EM black holes and neutron stars also here on the plot so that we can start to understand where interesting regions of this diagram are, these mass gaps that are very interesting, and also up here at the top, these very high mass sources that are being detected by gravitational waves that we had never have seen before using electromagnetic radiation. And so this is starting to become a really rich data set. It's very exciting. And it's also, for those of us that are eager to do electromagnetic follow-up for these gravitational wave sources, it's starting to be a little bit terrifying. Hence the sort of theme of preparedness and thinking about how we're going to tackle this problem going forward. So this is an older version of this, and I just wanted to highlight two of these particular sources. This is GW 170817. It was the first neutron star merger detected, and all of you have heard about it a lot. And again, Ralph will tell us even more today. And then another source that garnered a lot of attention during 03 is this candidate first black hole neutron star merger. And so you can see this is one of those question mark sources. So we're not quite sure whether the lower mass object was a black hole or a neutron star in this particular merger, but it was very exciting to the electromagnetic follow-up community, because if it is a neutron star, there's a chance it might be tidally disrupted and generate a kilonova type explosion and yield an electromagnetic signature that we could follow up. And the other thing, so let me just dwell for a second here on the kilonova side of this. So Indeed, this is a plot showing you some of the different types of components of a kilonova. The infrared, sorry, my video is a blue, a red, and an infrared component from Fernandez et al. That we might expect from a black hole neutron star merger, a kilonova-like signature, similar in some ways to the ones that we saw for the one instance that we have for GW 170817. We think there might be some slower fading in the IR and red wavelengths, which makes this an interesting regime to consider for follow-up for searching for EM counterparts. Of course, there are the same kind of viewing angle dependencies and things that we saw for GW 170817, which make these trickier sources to predict and to make strong sort of estimates of what kind of fluxes we might expect as a function of time for these different types of sources. But it's an exciting new source type to explore and to model and to try to understand what's going on. So the other reason, so kilonovae, this is really exciting. We might be able to see one of these type sources via electromagnetic radiation. But the other thing that was really exciting about this particular source, this potential neutron star black hole merger, GW 190814, is how well localized it was. So this is actually one of the reasons that it garnered so much enthusiasm and attention from the EM community. So it's the first potential merger between a black hole and a neutron star, but it's also just extraordinarily well localized. At least I haven't looked recently in the new catalog, but at the time of its discovery, it was the best localized gravitational wave source we'd had, which makes EM follow-up much, much, much easier. And so this was exciting, and a lot of people got, enthusiastic, including our team. We went and we followed up this very interesting source with the Canada-France-Hawaii telescope. And you can see here our G, R, and I mosaicing. We tried to do very heavy tiling in the 50% confidence intervals and then targeting just brighter galaxies outside of the 90% confidence intervals. And as you all probably know, the moral of this story was that our search, which was one of the deepest in addition to DECAM and other very, very deep searches for an optical counterpart, none of them yielded a counterpart in this particular case. So this is still the sort of the next frontier for us to cross with electromagnetic and gravitational wave radiation. But it's very, very useful for us to be practicing and building our pipelines and trying to really understand how these follow-up campaigns can proceed and how we can do them efficiently. So this pipeline that my team worked on was a difference imaging pipeline. That's the same type of methodology that many of the different teams use. And I think it's exciting. It's a lot of work to go through these really, really large catalogs, to pick your galaxy catalog, to make sure that it's complete, and then to do all of your assessment of whether or not you've done the search in the right way. So we did manage to put some constraints, but they're not very tight constraints. So what you're seeing here are the some constraints on the ejecta, so on the ejecta mass, the eject velocity, and the optical depth. And so we can rule out a GW 170817 like mass and opacity, but you can see there's very, very large parameter space that's still available to us here. And so these models are only modestly constraining when we only can accomplish upper limits for searches like this particular one. So the other sort of theme that I want to pick up on and just talk about a bit here is that we're in this sort of moment in between 03 and 04, and we're anticipating having as many as 10 new neutron star, or neutron star black hole kilonova-like events or possibilities in 04. And that's going to be a huge rate. And these really ambitious, very, very deep, highly resourced searches are going to become more and more challenging. We also have LSST coming online. We had some talks that thought a little bit about, I should actually change this, sorry, it should say VRO. Thinking about how the Zwicky instruments and pipelines and all of the VRO stuff coming online, how that's going to be impacting our demand for follow-up observations as well. And so as we move into this domain where there's going to be a huge number of exciting transient events to follow up, we're going to need to start to figure out how to prioritize our observations and how to do the smartest possible searches. So one effort at this is work that's done. I spelled out Aaron's name here. This is a slide I borrowed from him. This is a collaboration that's really kind of arising out of the SWIFT telescope collaboration, and they've been trying to get people to at least put in their pointings for various different observations that are taken for these follow-up campaigns. So once again, this is GW 190814, that same source that my team helped to follow up as well. And I think Aaron's sort of mission here is to shame all of us to some extent for having all of our fields overlap when we do these EM counterpart searches. He really would like to see us all do a better job of trying to coordinate our resources so that we spread out and really fill out those 50% confidence regions, fill out those 90% confidence regions, and make sure that our campaigns are more complementary instead of duplicative. Obviously, every instrument has slightly different capabilities, and so it's not the case that every little pixel where you see many colors here is getting the exact same depth of data or the same wavelength of data. So there's quite a bit of optimization that needs to be thought through for these types of coordination efforts. But it is an interesting, I think, effort and an interesting thing to think about as we sort of anticipate entering into 04 and potentially, if we're lucky, into a regime where we have more sources than we know what to do with. So this is the GW treasure map, and I believe it's all publicly available. You can go out and you can add your data to this, or at least your fields of view if you're curious about it or you'd like to contribute. So another effort that's sort of along these same lines is many of you who work on these sorts of campaigns have noticed that we had some false alarms in 03, a few that were retracted sufficiently late in the game that we even started getting excited and calling Belinda and saying, hey, we might have some really interesting source, only to be then disappointed when it was retracted. So I've been working with a team at UBC, Miriam Cabero-Muller and Jess McIver, have really been thinking about how do we take these public alerts. So now LIGO-Virgo, CIERA are in this regime of giving a public alert, and can we take just that public alert data and do a better job of classifying those sources and determining which ones are the highest caliber sources for doing EM follow-up. LIGO has a sophisticated analysis, and they run multiple different pipelines, and they have their own thresholds for what they think is, a tolerable possibility that something will be retracted. But this is an opportunity to then now give a little bit more input to the system, potentially even thinking about some of the astrophysical options, where it is in the sky, how much extinction you might have, how good are your galaxy catalogs in a certain area, et cetera, to prioritize in the case where you have multiple sources or too many sources for the number of resources that you have been allocated to do follow-up work. So this is a picture here. This is, again, Miriam Cabero-Muller's work. This is one of the retracted events from 03. You can see here that this glitch is masquerading as a true gravitational wave source. For all of you that have looked at gravitational wave sources, it looks quite a bit like a regular chirp. And so she's been developing this algorithm called GW Skynet. This paper just came out a few days ago. It's only been out and accepted for a couple of days. And we were really thrilled that the 03 catalog also came out in the last couple of days. And so hopefully Miriam won't want to kill me for putting our Slack chat up here. But she was so excited when the 03 catalog came out, because it turns out that actually this algorithm that she'd been building did a very, very good job of identifying sources that were glitches, that were noise instead of real signal. And so in almost every case, this algorithm got it right. And it's really just a first foray into thinking about this. We'll build better training sets and do some better thinking about how much extra information we can extract out of the public alerts to do a better job for predicting what's going to be the most exciting gravitational wave follow-up event to throw our resources.
2 minutes.
I think I'm done. That was it. I have some slides about instruments, but I'm more than happy to talk about those as a part of our discussion later. So I'm happy to stop there.
Great, thank you. I'm sorry for interrupting right there.
No, it was perfect.
Great. Remember to put your questions into the Q&A box for our speakers, and be sure you address who the question is for. I'll ask our next speaker to start sharing their slides. Our next speaker is Brian Metzger from Columbia University and the Flatiron Institute, and they will talk to us about mapping the diverse outcomes of, I think that's, let me check what the acronym is.
Unlike Daryl, I expanded my title, so
Okay.
so I changed it slightly to, it was actually based on a CFAR meeting we had where I was asked to talk about what's left to discover, as we've discovered everything with 170817. And I want to build on the nice talks by Nora and Daryl, and talk a little bit about expected diversity and outcomes of binary neutron star mergers, and then hopefully say something about black hole neutron star mergers. And I'm going to frame this in terms of what we can learn about the physics. So basically we have a picture for what these outcomes are, and if that can be confirmed by observations, great. If it's not, we're going to learn something unexpected, and along the way we may learn something about the equation of state of neutron stars. And so I want to talk a bit about that. So this is a slide I had in my morning talk, basically saying, just reminding you what we learned from 170817. We learned that even if you're slightly off axis of a gamma ray burst jet, you can still see some gamma rays. They're not as bright. They might be delayed if my thoughts on that are maybe the jet took a little time to get out of the cloud of debris from the merger, but they can be delayed one way or the other. We can see this idea of an off-axis afterglow is real, and X-ray and radio observations really tell us, as Nora was describing, about the structure of the jet. Is it cored? Does it have a sheath around it? What angle are we viewing it? What's the density ISM? We can learn these things. And then we also saw the optical infrared emission, which told us that we had heavy element nucleosynthesis. And since we saw both the blue and red kilonova, so to speak, that tells us that some of the ejecta contained exclusively lighter R process elements, and some of it had some of the heavier elements in it, which I think is an important clue to how long took the black hole to form in this event. So as Daryl discussed, more mergers are coming. We just finished 03 prematurely due to COVID. There was a discovery of one more binary neutron star merger and one possible black hole neutron star merger. Unfortunately, despite heroic efforts, the follow-up efforts were not successful in the sense of no confirmed counterparts. There may have been a black hole merger counterpart. I'm not going to talk about that today. Very exciting possibility. But then, in a few years, we're going to have 04. Maybe, the rates are coming down on the binary neutron stars, but maybe we'll see one every few weeks, we could hope. Maybe once a month, we'll see. And then, LIGO has approved upgrades, which are going to take place probably close to the end of this decade. And, if they achieve those sensitivity goals, we could be seeing a merger every few days or every week. So we're going to have more mergers. We're going to see these events at different angles, events similar to 170817. We're going to see, more massive neutron star binaries, less massive ones. We're going to see hopefully more clear-cut black hole neutron star mergers. And I think, one of the interesting things that we'll be able to, either you can see it one of two ways. We don't know what the equation of state inside neutron stars are, so we can use these observations to learn something about that. On the other hand, our ability to predict the outcomes of these events, depends on this uncertainty. And so hopefully we'll be converging in parallel with our development of understanding what's inside neutron stars. So as you know, a given equation of state predicts some mass radius relationship. If it's ordinary nucleonic matter, they tend to be well-behaved equations of state like this. If you have quarks coming in, phase transitions, you can get weird kinks in these curves, which would be quite exciting if there was, at a sufficiently high density inside a neutron star, if there was a phase transition and suddenly this curve shifted, that would be pretty cool. But for a given equation of state, essentially you predict a radius and a maximum mass that can be supported by that equations of state. And we're beginning to learn some things about neutron star radii, of course, from NICER and from GW observations. We also have improving constraints on what the maximum mass of neutron stars are, that it has to be above 2.1 solar masses, which is a big shift from 10 years ago. And so these properties of the equation of state, which are encoded in things like the maximum mass and radius, end up affecting the outcome of the merger. So you have two neutron stars that in spiral and coalesce. It could take a long time for that to happen. The merger itself is happening very quickly. What numerical simulations find is that if the total mass of the binary exceeds between about 30 and 60% above the maximum mass of a single non-rotating neutron star, then the outcome of the merger is a fairly quick collapse to a black hole. Now, it isn't to say there's no ejecta. There's a tidal ejecta potentially. There's maybe a little accretion disk, but overall, it's a pretty dark event, we think. But for less massive binaries, less than this threshold, the outcome of simulations show that you produce a temporarily stable neutron star, which is not collapsing into a black hole because it's rotating differentially. Well, in particular, there's a lot of the outer layers are supported rotationally. But then we think over some time scale, due to viscosity in the remnant, possibly magnetic viscosity of sorts like the MRI, you'll get redistribution of angular momentum in this remnant and it will destabilize. But it will take longer than this case. It could take tens, hundreds of milliseconds. It's actually uncertain. But in this case, because you've undergone this redistribution of angular momentum, you end up forming a fairly massive disk. Basically, you push out angular momentum to collapse, and as a result, you make a more massive disk. And there's more ejecta. The neutron star itself can eject more material before it collapses into a black hole. But if you have a very low mass binary, which is less than about 20% above maximum mass of a single neutron star, then even once this object has come into solid body rotation, even once it's reached its minimum energy state for a fixed angular momentum, it still is not wanting to collapse. It has to actually globally lose angular momentum through, for instance, magnetic dipole spin down to collapse to a black hole. And that could take minutes, hours, days. It depends on how strong the magnetic field is, if there's any other loss of angular momentum, et cetera. And so what I want to emphasize here is you have extremely diverse outcomes for just like, 10% changes in the mass of the binaries. And so we don't, until we know what the maximum mass is and until we know what the population of merging binaries is, we should assume all of these are fair game for possible outcomes. And of course, LIGO and Virgo can measure the total mass of the binary actually very well. They could actually tell us this within a few minutes. If they to some accuracy, that's probably good enough for astronomers. And then electromagnetically, we want to ascertain what's coming out. They don't have a lot of sensitivity to what's happening over here yet. This is high frequency gravitational wave behavior over here to see a collapse or to see a oscillating remnant. Eventually they will, but for now, the electromagnetic observers are what's learning about the outcome. And then by combining these, that's the real promise of multi-messenger astronomy. So I just want to emphasize a few things. One is that there's a variety of different energy scales here. So if you collapse to a black hole promptly, the sum of your kinetic energy and disk winds and things is probably quite low. You also don't have much in the way of neutrino emission because you haven't produced a long-lived remnant. So the ejecta is less irradiated by neutrinos. And all else being equal, this tends to produce more neutron-rich ejecta, which tends to produce a redder kilonova. On the other hand, if you produce a long-lived remnant, it has a lot of rotational energy, 10 to the 52 or 10 to the 53 ergs, which it could tap into the environment and electromagnetic emission. And you also have a lot of neutrino irradiation because your object is surviving. These neutron stars are extremely hot. They're as strong as the neutrino sources from core collapse supernova. So the ejecta will be strongly irradiated. You'll have less neutrons in your ejecta, and all else being equal, you'll have a bluer kilonova. And then this case is somewhat in between. You get probably of order 10 to the 51 ergs in the sum of the kinetic energy in the GRB jet, and it's moderately neutrino irradiated. So 170817, there are many reasons I suspect that we went through this channel and formed a black hole fairly promptly. One thing is there was too much ejecta for it to be a prompt collapse. The quantity of the ejecta made sense as being an accretion disk outflow without, also, as far as a long-lived remnant, we did see some of the heavier R process elements, which I think are hard to produce if you have the amount of neutrino irradiation you expect from a long-lived remnant. And there are also, arguments I'll come to in a second about, we didn't see a gamma ray burst. Does that, we saw evidence for a gamma ray burst. Does that tell us that a black hole formed? It's not so clear. So in the future, what if we did see a prompt collapse? How would it differ from 170817? Well, as I mentioned, we'd expect less ejecta. So, it should be dimmer, probably producing a redder kilonova. And because the accretion disk is probably less massive, you'd kind of naively expect that the GRB would be less energetic. So we had a possibility to observe such an event in 03 with a 1904-25. As you're aware, the first neutron star merger, its total mass was smack dab in the middle of the galactic double neutron star population, whereas the second event had a total mass of above 3.2. Which is much more massive than the neutron star binaries in our galaxy. It probably was 2 neutron stars. We can't be 100% sure, but it would have been massive enough that it would have been in this prompt collapse channel. We would have liked to test this, but unfortunately, because only one of the detectors was at full sensitivity or operating, the CIERA regions from localization were enormous, and so nobody found a counterpart. But you wouldn't have been able to find a 72817 analog with 100% certainty over this large area region, and probably you're looking for something that was even dimmer and harder to find. So we could have tested this, but unfortunate bad luck. What about this supermassive neutron star? So if you had a lower mass binary that, as I mentioned, I'll come to this in a second, but probably you're going to get the bluer kilonova because more neutrino radiation. And you have more energy in total because the neutron star has a lot more rotational energy than, what we saw with 17817. But it may not come out as a gamma ray burst. It may come out as X-ray or radio emission, as Nora mentioned. So there's this question: can a magnetar? Do I need a black hole to make a GRB jet? And it isn't just a matter of energetics. The problem, and there are different ways of coming at this issue, and I should have cited more papers here. Apologize, but basically the problem comes because your remnant is a very strong source of neutrinos. And it blates baryons off of the surface of the neutron star. So any kind of jet you'd want to create has a limit on how relativistic it can get while your neutron star is still present. Now that said, over time, the neutron star cools, its neutrino luminosity drops, and it stops ablating baryons with time. And so your Lorentz factor of, say, the wind coming off or the jet coming off of this polar angle can increase and may become trans-relativistic on a time scale of a few seconds. So there's a possibility that if we didn't have an actual GRB jet, the transition, the cooling, basically the acceleration of this cooling magnetar wind could have produced, a shock breakout through the ejecta and gamma rays. This was also proposed by Belgorod et al. On this time scale. But then we did see the evidence for the off-axis, powerful jet. So I think if we hadn't seen the later off-axis evidence for a jet, I might have said, okay, maybe we didn't form a black hole just based on the gamma ray emission, because the gamma ray emission was constrained to be mildly relativistic. Anyways, it's hard to make a classical, high gamma factor GRB jet within the first few milliseconds. That said,
minutes, sorry.
Yeah, sorry. That said, it has not prevented us in the past from proposing this as a possible explanation for the extended emission after short GRBs. It could be you could get a jet here, and there's, as there's these short GRBs that have these tails of extended prompt emission. Could that be a magnetar? Maybe, but then we'd have to really say, how relativistic was the jet that made the initial prompt spike? So I'm basically finished. I talked during my previous talk about how, you could also get longer X-rays escaping from the nebula behind the ejecta in the case of a long-lived remnant. And we can also probe long-lived remnants through radio observations. This is Schroeder et al. Recent observations from VLA, upper limits on short GRBs. Okay, anyways, I'm running out of time. I took way too long. I'll simply say with black hole neutron star mergers, it's an all or nothing kind of game. You either tidally disrupt the neutron star outside the horizon, and you can get these same signatures, kilonova, accretion disk, or you swallow the neutron star whole. And to get the tidal disruption, what you require is a low mass black hole that is spinning in a prograde sense. You have to have, if it's not spinning, which we think many of LIGO's black holes are not spinning, you need a very low mass black hole, probably less than 5 or 6 solar masses to get a tidal disruption. Given what we know about neutron star radii. And so, we could get this signal, but, a lot of these could be dark, especially those with the massive black holes, such as we saw in 190814. I shouldn't deter astronomers for looking, because if you saw something in this type of binary, it would tell us that we know nothing about, basically neutron stars are much bigger or more tidally deformable than we thought. So that would be really cool. But, it's not too unexpected we didn't see anything from this first event. So I'm finished. I'll just say, just to reiterate this plot Daryl showed, which is our end game is to try to make an empirical mapping between gravitational wave signatures and electromagnetic signatures. And as we accumulate more events and we'll test this possibility that there's these different outcomes, that there are these prompt dividers between them. And as we tighten this, we'll be able to constrain equation of states parameters. But we also prioritize our follow-up. We may say, oh, that event was a prompt collapse. I'm going to need more resources to find the counterpart, or that was a long-lived remnant. I should use a smaller telescope. And eventually, we're gonna learn something here. If this is all wrong, it may point to something new, some exotic physics we don't understand. So I'm gonna just stop there. Thank you.
Perfect. Thank you, Brian. Will our next speaker start sharing their slides? Our next speaker is Raffaella Margutti from Northwestern University and the CIERA, and will talk to us about the bright future of GW 170817.
Thank you, Rudy, and thank you all for having me. It's very exciting. I hope you're seeing my slide right now.
Yes.
Yes, perfect. Okay, so I'll try to give you a complementary perspective on 1717, complementary to Brian, Daryl, and Eleonora's perspective. And particularly, I will try to emphasize what we could not constrain. So what are the limits of our knowledge on 1717 jet and afterglow parameters? So we have been observing 1717 in the last year with our programs, and I'm excited to share that our next observation is already planned. Big thank you to the Chandra team. It's going to be December 9th, 2020. These observations are public. We decided not to claim any proprietary right to allow all the community, the entire community, to take advantage from it. And I'm very excited to see that the community is really engaging with our data, as Nora's talk demonstrated. So here is a quick cartoon. We've been seeing that many times. I just want to emphasize the components of emission that were detected for 170817. It goes from the gamma rays to the kilonova thermal, the cocoon afterglow, and the collimated jet afterglow. And I want just to remind ourselves that a lot of these are firsts. So it's really the first time and only time that we could collect these photons. What are we waiting for? As Eleonora alluded to, we're waiting for the kilonova afterglow to maybe give us some more photons. So the multi-messenger picture that we put together is that of a normal short gamma ray burst very close by that was seen at an angle that is in between 15 and 20 degrees. So we were off axis. With this plot, I would like to emphasize something that maybe is not always well appreciated, that if you put together all the constraints that we have on the off axis angle, you will see that the gravitational wave based constraints and the light only constraints are in some sort of mild tension. So you can see that the afterglow and VLBI observations tend to favor a lower off-axis angle than gravitational waves. I'm happy to expand on that if you have questions of why that happens, but let's just keep in mind this. So here is where we are right now. You have a plot of the radio, X-ray, and optical afterglow of 170817 in these 3 years. It's a beautiful synchrotron emission, and I want to give credit to all the people in the community that contributed to really acquire this outstanding data set. So we have, to oversimplify the problem, we observed a very shallow rise that is actually telling us something very important. He's telling us that starting from day =9, we were already inside the cone of some material that was emitting. So we were off axis with respect to the core of the jet, but not off axis with respect to its wings. Then we have a beautiful peak around 160 days and a very fast decline, like T to the -2.2, that is telling us that now the emission that we are observing, it is indeed dominated by the core of the jet. So if we zoom in to now we are around 1,000 days after the merger. Chandra is the only observatory that was able to detect photons from this system. And you can see right away that there is a little tiny evidence for some slight departure, maybe from the jet afterglow model. I want to make it clear from the very beginning, there is no statistically significant evidence for it. It's very exciting, but we need to wait for more observations to be acquired to see if there is deviation or not. So where are all of these photons coming from? The picture that right now is accepted in the community is that at early times, we were seeing emission coming from the wider angle outflow. And at later times, we saw the emission coming from right from the core of the jet. While all of this is happening in the light curve, the spectrum knows nothing of it. So what you have here is a spectral evolution from radio to the X-rays from t = 9 days when we had the first detection of the non-thermal afterglow all the way to now. And you can see that early times the optical emission was dominated by the kilonova, and at 100 days, everything is the most beautiful power law, simple power law in the sky. So this is pure beauty, and from one perspective. From the other is actually a huge problem. So this is this very simple power law spectrum without spectral breaks leads to an intrinsically under-constrained physical problem. And here is what I mean. So if you try to model this afterglow data with a structured jet model, you are dealing with, at the very least, 7 unknown parameters that I try to name here. The off-axis angle, the jet angle, how wide is the cocoon, the density in the environment, the kinetic energy that you have in these components, and the shock microphysical parameters, epsilon b, how much energy we have in magnetic fields, epsilon e, energy in relativistic electrons, information about the distribution of electrons that are produced in this synchrotron emission, quantified by this parameter p, and also the efficiency of acceleration of electrons into the non-thermal power law tail. So if you do numbers and you look at this data, the number of observations constraints that we do have from the afterglow are n = 5. So you do understand right away that this is a system that does not have a unique solution. Anytime that you will see the literature, very nice distributions of all of these parameters, what that means is that there are hidden priors in the modeling. Specifically, I'd like to draw your attention to one thing. So we do know very well the ratio of the kinetic energy to density, kinetic energy of the jet to the density of the environment. And the reason why we know that very well is because it does determine the peak of the afterglow, as the peak of the afterglow is effectively the deceleration timescale. And these are the parameters that you will find quoted and all the papers that came out that tried to model the afterglow well after a couple of years converge on these numbers. However, the individual parameters are not as constrained. The other point I would like to come across is that all of these lines that you see, dashed lines, dotted lines, dot dash lines that I have in the plot of the afterglow correspond to jets that have different structures in terms of energy per unit solid angle and Lorentz factor as a function of the angle. All of these models can do a very good job in predicting what the afterglow is, which is telling us that effectively there is no way for us to really distinguish between the structure of the jet. Ultimately, the reason why this is so is related to the fact that first, the spectrum is effectively the most featureless spectrum you can think of, but also we do not have information about the initial parameters. We have no way to constrain the initial Lorentz factor, for example. So let me go back to this problem of not really knowing EK and N individually, but only the ratio. What that means is effectively that if we place 170817 on this plot of kinetic energy versus density, what happens is that the models that you will find in literature are very good in constraining like this band, because we can constrain well the ratio. But as I said, the individual parameters are way less well constrained. Thankfully, here, this is a place where Chandra can actually help us in a completely different way. So Chandra observations of the host galaxy of 170817 can actually help us understanding how much material was there in the environment of 170817. So what we did here is a study of the plasma emission from the host galaxy of 170817 that allows us to infer that the density most likely at the location of 170817 is below 10 to the minus 2 centimeters to minus 3. So if we place this constraint on this plot, this allows us to block out a portion of the parameter space. If we make, on your right, if we make some assumptions, some very reasonable assumptions, but still assumptions on the jet microphysics, on the shock microphysics, which is that parameter epsilon E.1, we can put a cap on the other side to then constrain the most likely place where 170817 lived. So where do we go from here? Here I want to make 2 points. So first of all, what is the future of 170817? Are there any hopes at all to have more parameters, to constrain more parameters that would allow us to then go back and refine our initial estimates of the jet afterglow parameter? And the second part is, of course, population studies. We have n equal 1 event with beautiful observations, but it's just one. How can we go about finding more? Today I will mostly focus on this first point, but I will conclude with a comment on what is the true challenge in trying to do population studies in the EM spectrum of neutron star mergers. As Nora was alluding to, just like any outflow of material that you launch into space, that creates a shock. It's almost impossible to avoid that. Shocks accelerate particles, and those are beautiful ways to produce synchrotron emission. That means that together with the jet afterglow, cocoon afterglow, we also have another component, which might be in the future the kilonova afterglow. The kilonova is much heavier. The ejecta is much heavier than the jet, which means that it takes a long time for the ejecta to decelerate, which means that it takes a long time for the ejecta to transfer the kinetic energy into radiation. And that's why the signature of this kilonova afterglow is expected to peak years after the merger. But we are 3.5 years after 170817, so maybe this is not such a distant future to think about. So the reason why we want to do physically is the following. So here is a plot of kinetic energy and ejecta velocity on the x-axis. And one of the key parameters is how the merger distributed this kinetic energy into the ejecta velocity space. For those of you that are supernova friendly, this will sound extremely familiar. Just like supernovae, also kilonovae put the bulk of their energy into the slow-moving ejecta. And that slow-moving ejecta is the one that we saw radiating the optical UV and near-infrared at early times. This is thermal emission that knows effectively nothing, or almost nothing, about what the faster part of the ejecta from the kilonova ejecta is doing. And what we want to do with this, with our monitoring in the next years is the following. We want to understand which of these profiles is the right one. So how did the merger distribute the kinetic energy into the velocity space? So we want to constrain the ejecta stratification index and understand what was the fastest piece of the merger kilonova ejecta.
3 minutes.
Thanks. And this idea in mind of this EK versus gamma beta translates into the observational phase space into light curves. It's still synchrotron emission. And here I'm emphasizing the radio for one good reason. So what you have is the jet afterglow in blue, jet plus cocoon afterglow in blue, and then you have the predictions under some assumptions, as I will explain, on the kilonova afterglow. And I want you to take home one message, that the way to play this game is actually to play it in the radio. Why? Because the peak frequency of the synchrotron spectrum of the kilonova is way closer to the radio than to the X-rays. And here is looking at the future where we would be with NGVLA if that will happen. So it would really place us in this unique position to do a beautiful monitoring of 170817. If we look at the same thing in the X-rays, and this is interesting because our last observations actually sort of showed a hint or a hope for this axis of X-ray emission to start to appear. Here is how the same plot looks. And here is, if you look at the future, what links can give us. So actually links would be able to monitor 170817 for 30 years, so until I retire probably. So here is the caveat. So the problem of jet plus cocoon afterglow was under constraint. This is even more under constrained. Second part, the statistical evidence right now for anything else than a jet being there is very marginal, to say the least. There are also other ways that we can flatten out the light curve that do not require kilonova afterglow. So all of this has to be taken into account. However, the very exciting part is that if we do assume that we did not detect any kilonova afterglow, we can start constraining the parameter space of this kilonova ejecta profile. And here is a complicated plot with many parameters. I don't care about you understanding all the different parameters. The key thing is that we start constraining this parameter space. And with future observations, we can rule out more. So here is where our approved observations fall. So stay tuned. And if I have 1 second more, I will also like to say that the future can be bright for 170817, but can be extremely faint for all the other neutron star mergers. So the reason is, there are two main reasons. The first is that neutron star mergers are intrinsically faint, mostly because the densities are so low in their environment. But also, we always have to keep in mind that the gravitational wave strain goes like 1 over distance, while any EM counterpart, any instrument, the sensitivity of any EM instrument goes like 1 over distance squared. So we really need to up our game in the EM world to be able to make the most of the discovery space in neutron star to star mergers detected through gravitational waves. And it is my way to thanks the Chandra team and all the other teams for helping us out with these observations. Thank you.
Thank you, Raffaella. If we have any questions for any of our speakers, I remind you to put them into the Q&A box. And we can now field those questions for our speakers. Oh, I have a couple of questions to ask. First, I wanted to ask Brian you a question. You mentioned that the LIGO black holes have no spin. Is that from the chirp signal? How do you determine that?
So I should clarify. The majority of the LIGO black holes do not have measurable spin aligned with the rotation axis, or at least it's consistent with being very low. Yes, and that comes through the gravitational wave signal. The spin adds some phase information, so they can measure the component that's parallel to the black hole spin fairly accurately, and that's the component that is sort of the most crucial. If you think the spin is aligned with the binary orbit of the neutron star black hole system, then that's the one that sort of determines disruption or swallowing the neutron star hole. But that doesn't necessarily mean, I mean, the ones they've seen are not obviously mostly in black hole neutron star binaries. That doesn't mean that the black holes couldn't systematically be spinning faster in the black hole neutron star binaries.
We have a question from Gregory Sivakov. This has been great for the neutron star mergers. I'm wondering if, given your experience with these sources, do you have thoughts on the best way to use Chandra going forward for neutrino sources as well as gravitational wave sources? I think that's for everyone.
Give us more TO time.
Yeah, I think it's localization, right, Greg and Ralph? That's the thing, is like the neutrino localization is pretty poor. I know that a lot of the folks that are part of the SNOOS network are trying to figure out whether or not that's the supernova early warning system. They're like, if they network together all the different neutrino observatories, they might be able to do better localization if it was a nearby supernova. For blazars, you know, Greg, you know better than all of us. Those are just, they're big error circles. It's really hard. It's hard to do the searches with something that's as sensitive but small field of view as Chandra.
Any more comments on the question?
I completely agree with Daryl. Apart from the joke, which is half of a joke, by the way, about more TO time. The other thing that I would mention is that I think going forward, it will be necessary to coordinate probably among all the people interested. And the reason behind our choice to give up proprietary rights is exactly that one, to allow people to take advantage at t = 0 from any information that is out there. things are moving fast, the transits are moving fast, and the more information that we have, the best it is to make the best choices, the most informed choices about what to do next.
Yeah,
I guess if
a
I
lot of-
can.
yeah, go ahead, Rudy. Please.
I was going to tack on to Greg's question and ask specifically, how would you prefer if you had localization done? I mean, like you mentioned, Daryl, Chandra is not going to be good at localization because of the field of view. But once you had localization done, then it's TOOs of monitoring or TOOs of quick response, short response, long response. How do you prefer?
So in the GW world, I would also like to know what information is available from the gravitational waves on the off-axis angle. I know gravitational waves are not going to give me an answer plus minus 1 degree, but knowing if I have to get on target now, if they know that the system is equatorial, like I know that getting on target right now is probably not a great choice, or I have to space out my observations in a different way. I think that would be a piece of information that I would find very useful. I know that there are problems why it is not distributed, but practically speaking, it would be useful.
I mean, I should say that there has to be a synergy or a connection between the two fields, because there's as you know, there's a distance inclination degeneracy. So they don't know the inclination well, but if you have a target, it can tell you what the inclination would be for that target galaxy. So you know, you need a way to say these are the candidate events. This one, if it's a candidate event, would be 30 degrees. This would be 90 degrees. And then if you say, okay, I want an observation of that one, then that would inform whether that one would be on axis or off axis. So I think that's the bigger issue. There has to be a two-way communication, and it's just there's a I mean, to be entirely frank, I mean, they don't want to give away the distance information because there's science with H0 and other things people want to do, and so it's like, how do you balance these things is a hard question going forward.
And Greg asks a follow-up question, and you've kind of touched on it a little bit, Brian. What are the synergies between the two areas? And I presume that's the neutron star and the gravitational waves, or is that right, Greg? Yes, neutron stars and gravitational waves.
I mean, I talked a little bit about, I think it depends on what aspect of neutron stars. If you're talking about like equations of state, I mean, obviously LIGO can, put constraints on the tidal formability of neutron stars and neutron star radii, and obviously we're getting at that question differently through electromagnetic observations of neutron stars. And then as I talked in my talk, these different outcomes of the mergers depend on things like the TOV mass of the neutron star. There's a lot of messy physics connecting what we see and what those constraints would be. But I think that's that's one connection is we don't have many ways to actually put upper limits on the maximum mass of neutron stars other than through this electromagnetic. We can measure pulsars of increasingly large mass, but we're never going to completely know what the upper limit is. So that's the nice thing about this technique. It may tell us put an upper limit on the TOV mass. Yeah.
And Greg did re-clarify that he means the synergies between neutrinos and gravitational waves.
Neutrinos. Oh, sorry.
That sounds much more like the question Greg would ask. Greg, I don't know exactly what you're thinking about, but I know that there are lots of, one of our speakers earlier today talked about AMON, this effort to try to cross-correlate subthreshold signals from different experiments, so neutrino experiments and gravitational wave experiments. If you got lucky to have a nearby asymmetric supernova, right? Everybody would love to see that, like at t=0 or t=- something, and watch the whole evolution and UV and X-ray and neutrinos. It would be amazing. So there are plenty of synergies, but I'm not sure that we actually have the capacity to get on these sources to localize them. So the question was, if the localization was just known, that to me is like a huge if, right? I mean, you'd have to know really, really well if you wanted to get right on the sky. So a large field of view would help if you design an experiment to do that well, a telescope to do that well. So I think there's a lot of ideas out there for doing the kind of rapid follow-up. better, but they're kind of work in progress in a lot of cases, I think.
Yeah, we had a nice talk from Greg about the SmartNet, and I'm going to let Greg talk. He might have something to say about that right now.
So
Greg, if
this was actually just, I wasn't going to go into the SmartNet route, but this was just the general comment that there's so much great work going on with the gravitational wave follow-up, and the neutrino follow-up is in some ways almost orthogonal in nature, in the sense that we don't know the astrophysical sources that are likely going to be the cause of this as well. But there's got to be ways in which we can unite the two groups for, I think, better work across the multi-messenger era. And, you know, obviously, you know, the holy grail would be a gravitational wave neutrino event. But even without that, you know, the question is how can we take the best practices from one field and apply it to the best practices of the other, and apply it to the other fields?
How open is IceCube with its information?
So the IceCube, the IceCube people released their information very rapidly, as was discussed in some of the talks earlier this morning. And then, you know, as Daryl mentioned, there is a question of localization. However, as we find out more about the TDEs, CFERs, and blazars that are likely to be these sources, you can imagine that you take the results and run it through some simple queries to identify sources, so you could potentially rapidly get on them. It's not a slam bam, thank you ma'am type of approach, but it may be the way we have to go.
Faye, do you have any comments on the IceCube data availability? Faye from our earlier session is in the audience.
Hello.
Hi.
So the thing with IceCube is I'm not a member of IceCube, so I cannot speak to
Okay.
which data will be available. I've been using public data, and they have been making a lot of their data public, but I cannot address what they will make public in the future, unfortunately.
Okay.
And I think one of the interesting things from Anna's talk is, and I don't know if I believe it yet, but this, you know, association between neutrinos and tidal disruption events, and you know, is there a way to you know, because we're learning more about tidal disruption events from X-ray and from optical. You know, is there a way to test that hypothesis? Is there anything we can do? You know, I don't know what it would be, but you know, if you suspect a specific type of source, what can we do other than observe more TDEs to learn more about them? But you know, I found that was an intriguing. You know, now that they have the two candidates, quite interesting.
Great. Okay, I have a question for you all. You all played a major role in using Chandra to observe and study the first binary neutron star merger, GW 170817. We want to know what worked and what could be improved in the way that happened.
So shall I start? Well, I think many things worked. One is, for example, that data are available soon after the observations, and there is not like week-long delay. And so this is very important to have data in nearly real time. So that was definitely important. What could be improved? I totally agree that there are so many constraints on TO that many of the maybe explorative observations cannot be done. So sometimes we have to kind of bet on the most secure science just because there is a limit to the observation. So you want to go on something that is nearly secure result. And this does not allow, for example, to probe the early time after the merger. For example, in GW17817, there is a 7 days gap in which we don't have any information. And actually, this is a really nice spot because the afterglow was probably faint. And so we could have seen if there were other emission components not related to the afterglow. But because of the constraint in TO time, it was not possible to observe in that range.
We actually observed with Chandra 2 days, right? It was a non-detection. So I guess the point would be to have a little bit of a follow-up in between, like between these 2 days and the 9 days. It would have been, well, maybe it's easy to say right now because we saw it. I mean, it's easy right now. But going back in time, yeah, I agree. I would probably try to repoint in between these 2 days and 9 days for sure. I completely agree.
So, but even for future, you know, the number of fast TO is limited. So we probably have one approved fast TO for 03, and the other ones were like 15 days gap. So this is something that could be improved.
Great. Any additional questions from our attendees? If not, I would like to ask another question. Going forward, what discovery or discoveries are you most excited about regarding the study of X-rays from gravitational wave events?
I'll go with the kilonova afterglow.
I was going to say a kilonova from a black hole neutron star merger. There's lots of things to be excited about. We want to see X-rays from everything.
Mm-hmm. I would like to see really low mass binary that everyone can agree produced a long lived remnant, and just see how it differs. You know, did it make a jet? Did it make a GRB? Did it make an afterglow? I mean, did it make a kilonova? How's it different? So I think, that would be very exciting. If we saw something qualitative, like, okay, wow, that's completely different than what we saw from 170817.
Yeah, I agree that if I had to choose, seeing X-rays from the remnant object, like and understanding whether this might be a neutron star or a black hole, I think that would be my preference, because it would be unique to X-rays.
I mean, as I mentioned, that this puzzle of the extended X-rays and plateaus has been around for a long time, and now we've connected mergers to short GRBs. We have no clue what makes this extended X-ray. Is it related to the jet? Is it from a central magnetar? I mean, I think this is very interesting.
Great. I'll ask one more question. Well, let's see what Greg asked first. He completely supports the idea of more rapid TOOs for Chandra. I think that this conference demonstrates that we need to work on automating TOOs more for Chandra. And I know Joshua Wing, who is a Chandra mission planner who spoke at one of our panels, if you haven't had a chance to listen to it, is working on this to some extent, but that it is the only way that we can get more constrained TOOs, which is critical for all of time domain astronomy. It's more of a comment. And yes, I think that that has been demonstrated clearly by the subject of the talks that we've heard this whole session, this whole month-long session. That brings my question forward, which is what synergies with other facilities or joint programs are most useful for this science? And are there synergies that do not exist that would be extremely beneficial to do the science?
Yeah, I guess we want to get on target at the same time across the spectrum. That's the synergy that we want. So speaking from the perspective of somebody who puts in a ton of proposals, I would say that usually for each call of proposals, you know that I can propose to A, B, and C, but D is not allowed. And then you start to put together the puzzle of the things that you need, proposing multiple times. The dream of many observers, if not all in time domain, will be to have one proposal that gives me access to all the facilities at the same time done.
So something that might be coordinated by the observatories to
because sometimes there are joint programs, but then you have constraints on what can't be done on the other facility. Yeah, that's my personal view.
Raf just wants to take over the whole world. Like, give it all to me. So I'm not sure exactly, you know, we don't know yet what all the capabilities of JWST will be, but right now I know that that's not a place that you can do joint observations. And I think they are doing joint with Hubble, you know, and there's no way that's not on the minds of people in NASA and thinking about what could be done. But, you know, in the cases where you are looking for something really faint, which I think Raf made a good, you know, statement about that, right? 1/r versus 1/r². We're going to be going after really faint things, and we're going to need the deepest observations we can get, I think, in some of these cases. So being able to bring in those space-based observatories that are really, really sensitive and can go deep is going to eventually become important if we can get it up there and get it working.
Yeah, I think Chandra has a pretty good synergy joint proposal. They basically allow for time on pretty much everything. But for our studies, I would say the joint observations with radio is very useful. There is a very complementary nature in radio and X-ray studies. So maybe, I don't know, adding ALMA to BLA could be useful as a future thought. But in general, I have to say I'm quite happy with the joint GI program. So I find it well done.
And Raffaella, you mentioned that, you know, the simultaneous observations, that you do mean like simultaneous at the same time, and contemporaneous is not sufficient?
Oh, no, sorry. And what is simultaneous? It's actually a definition that varies depending on what we are talking about. And it actually depends on the age of the source too. So usually when I think about simultaneous, it means within a delta T over T, where T is the age of the source, within 10%, it's usually fine. But what I was thinking about is when I think about all the programs I would like to have, I also think about low frequency radio. Like GMRT, ALMA, that was mentioned by Eleonora. So instead of having to apply n times, it would be awesome if we could have one, because effectively the scientific cases are usually very, very similar. But yeah, and not complaining about Chandra, but if you want to do better, yeah, yeah, thank you.
Yeah, I think at the closing session after this, we'll hear more a little bit about some of the ideas that we've heard from everyone. Mike Novak made a comment that the last recommendation in the last senior review for PIs of the various missions to get together and discuss ways of coordinating joint proposals, at least for major topics like gravitational wave follow-ups more globally, which I think we all agree is a good idea.
I do think it's a challenge, just since I also do coordinated observations with the Event Horizon Telescope. Who's going to follow whom gets sticky when you start getting into, you know, and LIGO and, you know, other experiments are like this too, right? You know, who is the sort of driver, who's the most valuable resource that is going to sort of dictate the schedule and then have people adjust to it. And I think that there are parts of that, as Mike pointed out, that really should be done at sort of the level of PIs of missions, because it's not always driven by science, right? It's sort of driven often by scheduling and sometimes by a sort of perception of which is the more valuable resource or the more expensive resource. So
I think for Chandra, scheduling and the spacecraft constraints are the most telling for us. Okay, do we have any more questions? Mike adds that it might be easier to have a separate panel for a small handful of topics separated from the normal proposal route. That's an idea for sure. I don't know how feasible that is with our current peer review structure. Okay. All right. Well, I think that's been a good, healthy discussion. Do you have anything to say to each other or anything you want to talk about before we depart?
I guess everybody wants to, I would like to thank all the schedulers on Chandra's side for all their job. We are really, really grateful for this work that goes undetected sometimes. So really, really appreciative. And we know that we disrupt everybody else. So thank you.
Yeah, ditto to that 1,000 times.
Yeah, I think they are doing an excellent job, and it's a very difficult and hard job for sure. Okay, great. Well, thanks again for joining us for this panel discussion on multi-messenger astronomy. I hope you can join us for our last session of the entire month-long workshop, which is at 2 p.m. Eastern time, so an hour and a half. You should have received a link for that. And thanks again for joining us, and I hope I can see you there. Bye, everybody.
Thank you.